Agreed.
Yeah, no problem.
All right, so to start out the interview, what interests you the most about studying Jupiter and working on the Juno project?
That's a good question. It's hard to answer on a Monday. Um, let's see. I'm really interested in like Jupiter's weather, like Jovian meteorology, basically. And I work on like the color and structure of the clouds. So I think it's really interesting to try and figure out like what the clouds are made of and where they are. And like because on Earth, right, we're able to measure everything directly because we're literally sitting in it. Whereas at Jupiter, right, everything we measure is remotely imaged or like remote sensing, and that like complicates things a lot, basically. So it's like it's a complicated problem, but it's like a fun puzzle to figure out what's going on, basically. So, and Jupiter, right, like doesn't have a surface, so the meteorology is really wild. It's all like, driven by heat being transported up from deeper in the planet. And so everything we measure about the clouds and meteorology and like what the weather's doing can teach us about what's happening deeper in the atmosphere. So that's why I really like studying that.
That's really cool. So for my second question, what are some of the most important discoveries that Juno has provided about Jupiter's atmosphere?
So let's see. So what has Juno done? At least what's relevant to my research is Juno has this instrument on board that measures radiation from deep in the atmosphere. And using those data, it's figured out that so we expected one of the uppermost cloud layers is made of ammonia ice, and everything below that cloud is supposed to be this like uniform ammonia gas, basically, right? And that's what we were expecting. But Juno, using that instrument, found that that was not the case. There's like this big column of ammonia gas right below the equator, but it's kind of depleted everywhere else. And so that's a sign that like something really complicated and weird is going on. So we think that Jupiter has these circulation cells that are kind of similar to those on Earth. They're called Hadley cells. They kind of spin around like this, basically. And so we think that there's something pulling ammonia up from deeper in the atmosphere, but then depleting it everywhere else. Which yeah, I guess isn't significant in the grand scheme of things, but at least for my research, it's important because it really informs how the clouds form. If there isn't that ammonia gas present to condense into a cloud in a given region, it's like, how did that cloud get there? So what are the other big things that Juno's figured out? I don't know. I'm still drinking my coffee, so I'm trying to remember. I don't know. It's looked at it looks at the gravitational signature of the like density distribution inside the planet because it goes really close to Jupiter when it flies by. So it can actually sense little changes in the gravitational field of the planet based on like changes in the interior of the planet. So it's trying to figure out what the core is made of, basically. And they're starting to really narrow it down to what the core, like how it's the structure of the core, basically, which is interesting. We might need more time and more measurements in order to be able to do that. But those are the two things off the top of my head. But yeah, Juno's been doing lots for a long time. So they figure some things out for sure.
That's really cool. And so what are some of the most difficult challenges that has come with studying Jupiter?
So the main thing, specifically with the project that I work on, we have this really big issue called degeneracy in our models. And it's basically the fact that, so when I try to reproduce like observed spectra of the atmosphere, you have to make like a model atmosphere in your computer, basically, and then calculate what the light will be like reflected off of that model atmosphere. And it's supposed to match what you see, basically. So the problem is a lot of these qualities of the clouds in your app in your model like they can account for each other, basically. So like you'll have like a cloud of like a given density with a base like at a certain pressure, but you can lower the cloud base but increase the density of the cloud and you'll get like the same result out, basically the same spectrum. So you can't really tell the difference between those two solutions. So, that's the case for like a lot of different stuff. So it's actually really difficult. That's like the main difficult thing to do, is like to pin down the like true solution. Some people are better at it than me, but I think that's like the main challenge, yeah, is working with that degenerate parameter space.
And also, how does your research on Jupiter's atmosphere help us to better understand gas giant planets?
That's also a good question. So all the gas giants are slightly different, right? But Jupiter is the biggest one, and it has kind of the most. So I mentioned earlier, right, that there's heat coming up from deeper in the planet that drives the weather, basically. Jupiter has the most heat, the most internal heat of any of the gas giants. So in that way, it's kind of representative, or it makes it easier to kind of figure out what's going on at Jupiter, and then we can say, okay, well, at Saturn there's something slightly different going on, but like maybe the same sort of weather systems are over there. Jupiter's also close, like physically close to the Earth, which makes it easier to like observe, like literally like on a like Uranus and Neptune are so far away that pointing the same camera at those planets than at Jupiter, like they're just like tiny dots on the camera, so like they're just harder to see. I think the other main thing too is that Jupiter, there's a lot of exoplanets that are Jupiter sized. And just based on their size alone, we can guess, right, that they're probably very similar to Jupiter. So the more we understand about Jupiter's weather systems, the more we can understand about exoplanet weather systems, which is, a whole other like regime of stuff we don't understand. So I think so it helps us understand not just the gas giants in our own solar system, but other exoplanetary systems too.
And what are some of the most exciting or unexpected discoveries you've made during the Juno mission?
So the work that I've been doing has been mostly ground-based support of Juno. So that means that we have been using like telescopes on the Earth to observe Jupiter while Juno's done these like close flybys of the planet, in order to like provide the canned language we always use is like provide global context and like expand the spatial resolution of the Juno mission. And so we look at Jupiter in slightly different wavelengths, and we also look at we see the whole planet. So Juno flies really close to the planet, so it only sees like a really narrow swath of the planet, basically, because it's like right up next to it. We see the whole thing. So if Juno sees a weird cloud feature, we can say like, oh, like that's probably the result of this big storm over here causing turbulence, whatever. So that being said, I'm looking at like visible light, like light our eyeballs can see, basically, right? So I work on characterizing the color of the clouds, like I think I said that earlier, right? And really the most interesting thing that I found so far is that up until recently, we've thought that, blah, blah, blah. I'm kind of giving a lot of context for this, but the kind of a big outstanding question for a long time has been what actually makes Jupiter like reddish brown. Like we don't know like what makes the great red spot red. That's like the tagline we use all the time. But there's been a lot of work into that recently, and we think we've identified like the chemical compound that like causes that. But recently we found some evidence, we're working on a paper that says that it might be the same compound or come from the same like reactants, the same gases, but that the longer it gets zapped by like ultraviolet light from the sun, it like gets more cooked and it changes color, it like gets redder, like darker. And so that's kind of a big deal, like in the context of what I study, because that means we could connect like the age of a cloud top to the color of the cloud top. And that would be a big deal, because then we could tie like, okay, so that like what's the overturning rate in that cloud? What's like the dynamical time scale there? And that can, tie itself to like what's the dynamical mechanism that caused that? What's the energy budget of that mechanism? So that like it trickles down to like all these other bulk planetary characteristics, basically. But it is difficult because of that degeneracy I mentioned earlier. The the color change can also sometimes be accounted for by changes in like the density of the coloring agent, right? So like we have to be careful. So like I don't know if like this coming up with like new colors to produce like accurate models is better, or just like it makes the problem more complicated. So we'll see. But if we could do that, that'd be really cool. Yeah.
And finally, what is your best advice for students wanting to pursue a career studying planets like Jupiter?
Like, okay, so here's my question. What level students? Because I think it depends.
Like college level students.
College level. I would say take take a lot of math classes, take a lot of physics classes, and if you can, take astronomy classes. Um, and I think the other big thing, work on your soft skills. Like I just talked with another group who also had recording issues, and I was telling them to like you need to like so as like scientists or as astronomers, we do like a lot of public speaking. We do a lot of it's like a lot of critical thinking, communication skills. We do a lot of writing. Like I've literally been only writing stuff like papers and proposals and stuff for the last like 2 months. So like, and I haven't been doing any science at all. So it's a big part of the job is like writing really convincing and clear and concise papers, basically. So that's like all very important. I think as an undergraduate student, if you can, getting involved in like a research project, either with someone at your university or there's different programs around the country that you can get involved in, where you can do like summer internships, different places. That's all very important and good. And I think like in general though, like I think I was telling this other group too, like being like perseverant is really important also. Like I told them that there's a misconception that you have to be really smart to work at NASA, and that's like not the case. You just have to like hang in there, basically. Like, and you have to push through when you're struggling, when you're having an issue, or like, and you have to troubleshoot it and figure it out and like push forward and make progress. And I feel like that's like more important than just like having book smarts. At least like all the people I've met are really good at troubleshooting. That's like the most important thing. So I think those are all little pieces of advice, but combined, I think they help a lot.
Well, thank you very much for your time. This was really amazing.
Hmm. Yeah, for sure. No problem.
I hope you have a good day.
Okay, you too. Okay, bye-bye.
Bye.